Hello, and welcome to this presentation, Understanding GPS Links and Codes. This presentation provides a short introduction to the links and codes used in GPS, or the Global Positioning System. Let's start with a brief explanation of what we mean by links and codes. Every GPS satellite transmits multiple signals on multiple frequencies. These different frequencies are referred to as links, abbreviated to L, and each link has a different number. The two main links are L1 at 1575.42 MHz and L2 at 1227.6 MHz. Newer GPS satellites also transmit on the L5 link, or 1176.45 MHz. On each link, multiple codes are sent. The two main legacy codes are the CA code and the P or PY code, while newer satellites transmit newer codes, such as M code, L1C, etc. In this presentation, we'll explain what these links and codes are and how they're used. We'll start with links. All GPS signals are transmitted within the so-called L-band on frequencies between 1 and 2 GHz. The main reason that L-band was chosen for GPS is the high code rates used in GPS require a relatively high bandwidth, about 20 MHz. This may not sound like much by today's standards, but back in the early days of GPS, that is, the 1970s, L-band was still relatively unused, and therefore a good choice. There are some other reasons for choosing L-band. First, signals are essentially unaffected by weather. L-band frequencies also don't require directional antennas for reception, something that's important in a mobile GPS receiver. And lastly, ionospheric delay at L-band frequencies is manageable. More on this shortly. And if you're wondering why GPS links have somewhat odd-looking frequencies, there's a simple explanation. They are all integer multiples of 10.23 MHz, the frequency of the atomic standards carried on board each GPS satellite. The reason for multiple linked frequencies is ionospheric delay, which is the greatest source of error in GPS. Signals from GPS satellites are delayed as they travel through the ionosphere, and this delay varies with both time and location. This delay is also frequency dependent. The lower the frequency, the higher the delay. The difference is, however, related by a simple scaling factor. What this means is that a dual frequency receiver, that is, one that measures signals from two links, can use this scale factor to remove and correct for most ionospheric delay. The greater the separation between the link frequencies, the better the correction accuracy. There are also other advantages to having multiple links, such as resistance to jamming and redundancy. All GPS satellites broadcast on both L1 and L2, and each link carries multiple codes. On L1, we have the CA or course/acquisition code, which is an open or unencrypted code. L1 also carries two encrypted codes, the P or precision code and the newer M or military code. And there's a newer open civilian code on L1 called L1C. Likewise, there are multiple codes carried on L2. The P and M codes are also transmitted on L2, as is the newer L2C civilian code. At this point, however, it would probably be a good idea to explain what a code is. As you may have noticed, all codes are identified by a letter or combination of letters and numbers. Codes are essentially a repeating, known, pseudo-random bit sequence sent at a defined rate and with a defined length. In GPS, you'll often hear the word chips used instead of the word bits. All GPS satellites transmit simultaneously on the same frequency, but they can be distinguished based on their unique code or segment of code. Here, one satellite, Space Vehicle 14, is transmitting one code, while another satellite, Space Vehicle 9, is transmitting a different code. How are codes used? A GPS receiver acquires a satellite or code by generating a local replica of each known code, and then aligning it with the incoming code. This is done through a process called cross-correlation, and a sharp peak will occur when the received code and the local replica are aligned. Successful correlation provides the signal delay, which can then be used to calculate the distance, or more properly the pseudo-range, to each satellite. With multiple pseudo-ranges, the receiver can then calculate its position. Let's visualize how this works. First, we generate a local replica of a satellite's known pseudocode, and then we slide the received code and replica codes past each other and calculate the cross-correlation. The offset between the received and replica code provides us with a signal delay, which is used to calculate the range to the satellite. The length and rate of the code have significant impact on how easily a signal can be acquired or tracked, especially under non-ideal conditions, or in the presence of noise, interference, or low received signal power. In general, the faster the code or chipping rate, the wider the signal and the sharper the correlation peak, which in turn leads to higher position accuracy. There are also several more esoteric aspects of code length. First, longer codes have lower cross-correlation, meaning lower mutual interference and better accuracy. On the other hand, longer codes require greater processing power. This may not be much of a concern today, but the relatively short length of the CA code, 1023 chips, is partly due to the limits in processing power in the 1970s. The most fundamental of the GPS codes is a CA, or Coarse Acquisition Code. This is the code used by almost all consumer GPS devices. As we mentioned earlier, each GPS satellite transmits a unique CA code, which unambiguously identifies each space vehicle and is therefore used to distinguish or differentiate between satellites. We call these codes coarse acquisition for two reasons. First, they're called coarse because their slower rate and shorter code makes them less accurate than the higher rate and longer P, or precision, code. The acquisition part of the name comes from the fact that these codes aid in acquiring P code. You may also hear these codes referred to as PRN codes or Gold codes, the latter being the name of their developer, Dr. Robert Gold. The CA chipping rate is 1.023 megachips per second, meaning that the sequence of 1023 chips repeats once every millisecond. In practical terms, a chip corresponds to a distance of about 293 meters. P code, or precision code, is transmitted on both L1 and L2, and contains essentially the same information as the CA code. However, P code is much longer and faster than CA code. This longer code and higher chip rate mean that we get a more precise time and range measurement, about 10 times better than the coarse or non-precision code. This tenfold increase reduces the distance of one chip from 293 meters in CA code to only 29.3 meters in P code. An adversary could potentially generate GPS signals in order to spoof a receiver and cause it to calculate an incorrect position. Anti-spoofing involves encrypting the code so that a receiver with the correct key can distinguish between real and spoofed GPS signals. When P code is encrypted, it's referred to as PY code, and only authorized users can obtain this key from the U.S. Department of Defense. Real-world P code is always encrypted and transmitted as PY code, but many PY receivers can actually be tested by sending them unencrypted P code. You may recall that the A in CA code stood for acquisition, because military PY receivers were originally designed to acquire the shorter CA code first, and then acquire the longer PY code. However, technology advances have made it possible for some receivers to directly acquire P code without having to acquire the CA code first. This is useful when CA code is unavailable, for example due to jamming. P-wide code has been around for a long time, and a newer code called M code is now being introduced to replace it. M code has several important features. It's transmitted on both L1 and L2, it has increased power to make it more jam resistant, it's designed for direct acquisition, and it's also designed to coexist with current GPS codes. In the United States, military GPS equipment will, eventually, be required to support M code. In terms of open or non-encrypted codes, there's also a new civilian code on L1, named L1C. This code is supported with the Block 3 or latest generation of GPS satellites. The biggest difference between CA code and L1C is that L1C uses a different modulation type, and the reason this modulation was chosen is that it allows easier interoperability between GPS and Galileo, the European version of GPS. Long-term, there are also plans to use similar modulation in other global navigation systems, like the Chinese Beidou and the Japanese QZSS systems. Likewise, there's also a new civilian code on L2, called, not surprisingly, L2C. Satellites launched since 2005 all transmit the L2C signal. The main reason for L2C is that having a second unencrypted link allows civilian GPS receivers to correct for ionospheric delay, thus increasing accuracy. There are actually two L2C codes, both with the same chip rate but with different lengths. L2CM sends navigation data, that is, information about the GPS constellation, at a slower rate, which makes it easier to acquire the satellites, especially when coverage is poor. L2CL has an extremely long code length, which provides better correlation and tracking once the satellites have been acquired. The only issue with L2C is that it's not in a so-called protected band. In other words, these frequencies are shared with other services. L2C can be used for some applications like surveying, but can't be used for more critical services like civilian aviation or safety of life applications. The newest member of the GPS link family is L5, which was implemented starting in May 2010. Unlike L2C, L5 is within a protected band, and this means that L5 can be used for civilian aviation or safety of life applications. Having L5 as a second unencrypted link provides both redundancy and high accuracy through ionospheric delay correction. In fact, L1 and L5 are farther apart in frequency than L1 and L2, so L5 allows for more precise ionospheric correction. And lastly, note that L5 is both the name of the link as well as the name of the single code that's sent on this link. So we have L1, L2, and L5. What about L3 and L4? Actually, GPS satellites do transmit signals at frequencies referred to as L3 and L4. The L3 link supports the Nuclear Detonation Detection System, or NuDet, and L4 is used for research into methods of correcting for ionospheric delays. Because neither L3 nor L4 are used for navigation or timing, we won't be covering them in this presentation. So let's review the links and codes used in GPS. On L1 we have the CA code, which is used by almost all civilian GPS receivers, and which is also used to acquire the higher precision, but encrypted P code. L1 also carries two modernized codes, the updated military M code and the civilian L1C, which is designed to interoperate with other global navigation systems. On L2, we also have the P and M codes, as well as the newer L2C codes, which allow for civilian ionospheric correction, but are not suitable for aviation or safety of life applications. Finally, the new L5 link carries a single code, also called L5, which provides civilian ionospheric correction and which is in a protected band, and thus can be used for aviation or safety of life applications. So in summary, every GPS satellite transmits on multiple frequencies, or links, and each link carries at least one, but usually multiple, codes. Codes are used in two main ways. First, they identify the individual satellites, since each satellite transmits a unique code, and code delay is used to determine the range, or pseudo-range, to each satellite, which is what enables position determination. Using multiple links provides redundancy, but more importantly, it also allows for correction of variable ionospheric delay, which is the primary source of inaccuracy in GPS. And lastly, numerous new codes have been added to the GPS system over the last several decades, and these provide improvements and enhancements in terms of satellite acquisition and tracking, position accuracy, and interoperability with other global navigation satellite systems. This concludes our presentation, Understanding GPS Links and Codes. If you'd like to learn more about GPS-related technologies or test and measurement solutions, please see the links in the video description. Thanks for watching.